All right, welcome everybody to this robotics seminar series talk sponsored by Lockheed Martin. Today we have the great pleasure of having Professor Ames joining us to talk about his very exciting work on safety critical control dynamic robots. Professor Ames is currently a Bren Professor of Mechanical and Civil Engineering at the Control and Dynamic Systems at the California Institute of Technology. He received his BS in Mechanical Engineering from the University of St. Thomas, an MA in Mathematics and a PhD in Electrical Engineering and Computer Science from UC Berkeley in 2006. Dr. Ames served as a postdoc at Caltech from 2006 and 2008, and began his career at Texas A&M University. After Texas A&M, he jumped to the Mechanical Engineering and Electrical and Computer Engineering department at Georgia Tech, where he and I crossed paths for a little bit. And he was actually part of the doctoral dissertation committee, for which, again, I'm very thankful. Before joining Caltech back in, I think it was 2015?
2017.
2017. He's been the recipient of multiple awards, including the Leon Ashua Award for Achievement in Nonlinear Science, the Vernon Friedman Memorial Prize in Applied Mathematics, the NSF Career in 2010, and the Donald P. Ekman Award in 2015. His research spans the areas of robotics, nonlinear controls, hybrid systems, and specializes in applications of bipedal robotics, as you can see in his very interesting background. And so with that, I'm going to let Dr. Ames go ahead with his talk. Before we get started, I'm going to ask the audience, if you have any questions throughout the talk, please use the Q&A feature to post your questions, and we'll go and read those at the end of the lecture. The floor is yours.
Great. Thank you. Thanks for the great introduction, and it's good to see you again. As he mentioned, our paths crossed in Georgia Tech, which was, a great period. It's a fantastic place. And since then, I've been at Caltech working more on the same, which is safety critical control being one of the core themes and what I want to talk to you about today. So it's a pleasure to be here and talk. Again, I wish I could be there in person, but hopefully, soon I'll be able to visit Maryland. So with that, let's get started. So what's the goal of this talk? Well, before I talk about the goal, it's really important to talk about the students first, because really all the videos in this talk, all the results in this talk are only made possible by this group of people here, among others. There's actually a bunch of collaborators I worked with too, including Georgia Tech and now UC Irvine, Dean Magnus Egerstadt, and some videos with him are going to be part of this talk. So lots of people I've worked with throughout the years, but really the students are the highlight. And throughout the talk, you'll see links to papers where their work is cited. I really encourage you to follow up on those papers if you like the results or are interested, because this is really going to be a sampling of those different results in a broader theme. And so what's the theme? Well, the theme is robots are hard. Robots, broadly speaking, I don't just mean bipeds here. These could be flying robots, automotive applications, robots in the kitchen. There's a variety of ways we can think about robots in our daily life. But the one common theme of all these things is that they're difficult. And this is just some of the outtakes testing on Cassie. Either Cassie falls apart or Cassie steps on itself, or just things start falling off it. And they're just really difficult. Both, these are mechanical failures. There's also, of course, a plethora of algorithmic failures. Those are, in fact, the predominant failure mode. And the bottleneck in robots is the algorithms we're deploying on them. But then when they finally go, they're really, really pretty. So when things finally come together, they look really nice. So this is the end result of all that testing I showed earlier, is this Cassie robot with our walking algorithms. Specifically, these are Xiaobins, who's the one piloting Cassie back there, running below the surface, walking around the Caltech campus. And it looks like this is a super stable thing, and it is stable once we've gotten everything sorted out. It's a process of sorting it that's the challenge. But it's cool seeing where you can ultimately go with these things when everything works the way it should. It's also cool seeing kids' reactions. There's a little shot here. The kid just running around the corner trying to track down the robot, and super excited about it. So kids love robots. All right, so that's kind of the lesson here, is they're hard, but they work. And so what's the challenge? Well, the challenge is really to make them work every time, all the time, properly. And so I think of this as our canonical kind of application space in terms of getting things to work all the time. So Mars. And actually, I had a project with JPL on this coordination between the rover and the helicopter. It's not on Mars, but it was a proof of concept study from perhaps the next mission. And the idea was, okay, so we're developing all these autonomous behaviors on this system. How do we know that when we deploy them, they'll actually work the way we intend? And in this case, we can't do what I did in the previous video, where we can test in the lab a bunch, work out the bugs, and then make sure it works and then deploy it. So in this case, you have to have it right the first time without the ability to test in the real operating environments. And so how are we going to understand this framework? Well, the hint is here. And this is really, there's kind of two themes in this talk. One is safety critical control, which you're going to see throughout. But the way to frame safety critical control in a broader context, I think, is through these multiple timescales present on systems. So often in robotics and control, we focus on individual timescales. So we might be an expert in low-level control. So we love dealing with x dot equals f of x. And then we design controllers for these low-level control systems, and that's our focus. And that's great. And there's a ton of work to do there. Or perhaps we're interested in formal methods, or discrete abstractions, or MDPs, or planning, or RRT, or whatever your favorite sort of discrete representation tool is. Then in that case, you're kind of focused here. And the reality is, to get to this level of autonomy, we're going to have to cut across these layers. And these layers are not only varying between continuous and discrete, with the plant being sort of the most continuous object and the planning being the most discrete object, but they're also varying between the timescales. So typically low-level control and the plant itself operates at a much faster rate than the high-level decision-making. So the question is, how do we pull all these pieces together and start to think about robotic systems in a holistic way with a special viewpoint towards safety critical control? And so the goal of this talk is to kind of understand this and parse this up in a couple contexts. And I'm going to show a bunch of different applications of these pieces coming together. This is still an incomplete picture, meaning this is very much an active area on how to pull these layers together. I mean, so kind of a daunting task, because you're pulling all these different disciplines together in some holistic way. But the common theme is to make guarantees across layers. So make formal guarantees, specifically with respect to safety, across these layers in a unified way. And by doing that, we're going to be able to consider a variety of application domains, from walking robots, robotic systems more generally, all the way to robotic assisted devices, which will be the end of this talk. And then everything in between, being things like multi-robot systems and safety critical systems. So the idea is to kind of cover these two axes, where we're talking about safety in a variety of robotic systems, and the different timescales where the safety is operating, and how these integrate together in a holistic way. So that's where I want to go. And to start out, I'm going to start where I'm the most comfortable. So my background, my sort of passion is this low-level control. I love the clean statement of, you have some dynamics, it's an ODE. What can you say about this nonlinear system? And the key tools to do this that I'm going to talk about briefly here, and go into more detail, especially on the barrier function front, is we usually use things that are broadly called certificates to verify the properties of these systems. Things like Lyapunov and barrier functions, where we have a property, we want to verify it on this low-level controller, or this continuous dynamical system. So how does this look, and what does this look like? And then more importantly, this will be sort of the first chunk of the talk, but then I'm going to start transitioning into, once we understand this a little bit, how do we start to take these ideas up the chain? That is, apply similar methodologies or thinking, even if the problem descriptions are very different. All right, so to begin with, let's start with Lyapunov, because I think this is kind of the cleanest instantiation of what we do in control, and really, sort of a great representation of robotic systems meets control. So Lyapunov, of course, I imagine most of you are aware, is an old concept, 1892. Lyapunov formulated, and the idea is super simple. I'm actually going to not talk about Lyapunov functions, because I'm interested in control systems. So I'm going to talk about control Lyapunov functions instead. And this is a more recent concept, 1989, a la Sontag. And the main idea in Lyapunov theory, and any kind of Lyapunov-like representation of a system, is to come up with this low-dimensional certificate of the property that you want. So what does that mean? Well, you start with some nonlinear dynamics. And those nonlinear dynamics are potentially really high dimensional. So x dot equals f of x. X could be living in 50-dimensional space, 100-dimensional space. The dimension doesn't really matter. We will assume an affine structure to this system. That's really important. It turns out that's not a strong assumption because robotic systems, for example, have affine structure. And then what you do is you consider a Lyapunov function. So this kind of has two key properties. The first one is that it's positive definite. In this case, a bit stronger than positive definite. It looks like a bowl, like a quadratic bowl. And the second thing, and this is really the key notion, is that if this function decreases along solutions in a very specific way, then you can guarantee properties of the system. And the way we want to decrease along solutions relates to the property we care about showing. So in this case, if we care about stability, then we want this Lyapunov function to evolve as if it was a stable system. And in particular, here we have a stable linear system. So we have some constant multiplying v. So this is, think about this in the simpler way, just take away the v for a second. This is like x dot equals minus alpha x. So the simplest example of a stable linear system. And so if you can enforce this behavior, we have an inequality because we don't want to force exact connections, but rather just an upper bound on the stability constraint. If we force this, it implies that, of course, the Lyapunov function will be stable. And since this is positive definite, will imply in turn that your state is stable. And that's, that's sort of half my nonlinear control system course in 5 seconds, because that's the gist of it. Everything else is just about sorting out the details behind that basic conceptual concept. So once we understand this, we can say, okay, so now we have this certificate that's lower dimensional and verifies the property we want. What do we do with it? Well, what we can do with it is synthesize controllers. And so in particular, this Lyapunov condition, this derivative condition, can be represented more generally as saying, since we have an inequality, and since this input appears in the inequality, we can consider any control values that satisfy the inequality. And any feedback controller that's in that set will be guaranteed to give us exponential stability. So this takes away the notion of controller synthesis from being implicit, meaning you have to come up with a specific u of x that satisfies everything you want, and makes it implicit, meaning any controller that lives in this set will satisfy the properties we want. And that's a really important transition. It's subtle but important and not unique. I mean, lots of people have recognized this. Why is this so important? Well, then you can start synthesizing classes of controllers, and you can start to optimize your controllers, at least point-wise. For example, you can take a quadratic program, where given any other controller in your system, this you desired can be anything you want. You want to maybe match that controller subject to the stability constraint. So that you desired might be a joystick command from a person. It might be a variety of tracking the trajectory from a planning algorithm. And then you want to enforce stability in the constraints. And because of the affine dynamics assumption, this v dot condition, as you can see on the right there, is let me get up my laser pointer. There we go. So this v dot condition is affine in U. Hence, this is a quadratic program. And in fact, this has closed form solutions, which can be really simply stated as conditional statements. So that's the idea. And this is actually this controller implemented on the Segway verbatim, meaning we're actually doing sort of torque control using this this online, evaluating this quadratic program online. So that's the idea. And we've had a lot of success with this methodology. So we've applied these ideas, at least broadly speaking. The implementation details are not exact. So this isn't running the QP in real time on the robot. We actually use the QP to generate trajectories that we then tracked on the robot via PD control. Those subtle details are not hugely important right now philosophically, because the idea is, regardless of this, we're able to take this formal perspective and apply it to guarantee stability formally and practically realize that stability on really complicated systems. So this is an older video. This is actually at Georgia Tech, and I love this video because of the multi-contact walking we got. So this is a 4-domain hybrid system for those that know hybrid systems, and we have Lyapunov functions associated with all these domains, and we get exponential convergence and proofs of stability, and the end result is this nice walking behavior on the system. Okay, so the other important point is that not only can we do this on walking robots, and I'll show some other examples later, but these ideas, because we're framing them generally, can be applicable to a wide class of systems. So this is the same methodology applied to a quadruped. And so this is a bit older video now, but I like it just because it's very clean and simple. And the idea is super simple, where you take your quadruped, you break it up into 2 bipeds. Effectively, mathematically, you can do this. You generate walking gaits for those bipeds and make sure this connection condition is satisfied. And we can generate walking gaits using the full dynamics of the quadruped in around, in this case, 2.58 seconds. 2.58 seconds gives you this gait. So this is the power of taking this holistic approach. Again, I'm pushing a bunch of details under the surface here. I recommend you check out these papers, but that's the idea. And it isn't then restricted to a single quadruped. In fact, we've done this on a bunch of different quadrupeds. This is the same one, but now doing a robustness test. So this root system, you'll see this a couple times in videos. This is actually right outside my office. And this is sort of our true test of robustness, is make the robot walk over this. These are really deep roots. These are like 3-4 inches deep at points. So it's surprisingly difficult for robots to handle. And we can handle that robustly. We can also put this on other quadrupeds, like I mentioned. So this is the next, this is the Ghost Robotics quadruped, and this is their next generation. Interesting story is that the previous one, we were working for a deadline, this deadline, I think, and that robot broke about 3 days before the deadline, before we had any experimental results. And we sort of like, what do we do? And the students were like, well, we're going to try it on this new robot. They hadn't put any of our algorithms. Again, we're generating all of the walking gaits on this, all of the real-time controllers, everything. And so it's from scratch. And my students hadn't touched this robot yet. And they said, I think we can do it. In one day, they got it walking, got the robust gaits, took the video, wrote the paper, out the door. There you go. So it shows how when you do things generally without hacks, they work much faster in the end. And there's a lot of groundwork to get to that point. Don't get me wrong, a lot of infrastructure we already had in place, but that's the idea. Okay. And so going beyond quadrupeds, I just wanted to note that we've put this Lyapunov-like controllers exactly as is on robots too. So this is a more recent result. So a lot of the things I showed earlier, we're sort of doing trajectory tracking based on, simulations of the controller, but we're actually able to now really realize these QP-based controllers, Lyapunov controllers, on the robots in real time. So this is the actual form of the controller we're realizing. So it's sort of, you take into account the dynamics, you kind of shift things a little bit to be more conducive numerically. And the end result is that we can get this working on CASI. So CLF QPs running in real time. This is running at about 2 kilohertz on the robot, and we get stable, robust behavior. We're able to do a variety of different walking behaviors, forward, backward, side to side. We can even walk outside with these controllers. So this just kind of, again, I'm trying to illustrate this process, at least at a high level, of going from the math and the theory down to the robotic system. Okay, so these are just some other fun videos, samples of other things we've done. We can do robustness tests, we can do jumping, we can do fast walking, we can track trajectories. So we're starting to expand out the capabilities of these robotic systems beyond just, here's a great video of it walking in the lab, or a video of walking on grass in a very specific way, but rather, how do we make these things more general? Meaning we can actually deploy them in interesting scenarios. And so what you find when you go to deploy things in more interesting scenarios is that you often miss things, right? No matter how good your math was, no matter how robust your walking is, there's always these edge cases that mess you up. This is an example here. So that's that same root system I mentioned earlier. Now you can see it's a little bit, top-down view gives you a little bit of the depth. And what happened here is the robot's actually doing well. It's dynamically balancing fine, but it ultimately hits itself. So it has a self-collision trying to catch itself, which topples it. So stability is not enough. That's the lesson here. Stability, this is all stable. That's fine. We didn't violate the stability property per se. We ultimately did, of course, but along the way, we violated a different property that is in some ways intrinsic to having stability, and that's safety. That's staying within a set. So what we need is a more general notion than just stability to really make these robotic systems safe. And so this leads to safety critical control, and specifically control barrier functions. So these control barrier functions are actually a relatively recent invention from 2014, but that, as with every invention, they build on previous work that spans a long period of time, and the notions underlying them can be traced back to 1932, 1942. This is really the hallmark paper by Nagumu. And interesting enough, this paper where he gives necessary and sufficient conditions for set invariance, I'll talk about in a second, was lost to the ages in multiple occasions. It was rediscovered by Bonney and Brazos in the 60s. It was rediscovered by Prajna at Caltech in the 2000s. So it's been this thing that's been sort of rediscovered multiple times, but because the result itself is so fundamental. So now we'll talk about set invariance. So now things get interesting because now we're talking about newer stuff. And new, by new I mean a la about 2014. And this is work with Paulo Taboada and Jesse Grizzle. And so the idea is the setup here is we just formulated this notion of a CLFQP that I showed you earlier. And the question then was asked of us actually was, okay, so now that we have this notion of a whole wealth of control inputs we can pick, what can we do with this in a powerful way? How can we exploit that structure? And the answer, the idea was, can we think about set invariance and safety? That is, in this case, it's illustrated here, is we're not so much worried about the stability of the system. Sure, it has to be stable, but there's lots of controllers that can make it stable. The question is, given any of those controllers, whether it's a Lyapunov controller or maybe you're just doing an LQR controller, how do you keep it safe within this region regardless of what the controller is? And so by safety, I mean the following. I mean that we have some safe set C defined as a super level set of this function H, the zero super level set of H. So this is sort of understood as here's your safe set, meaning this ellipse. And the function itself is maybe this bump function, which when it's positive defines that ellipse. And so again, going back to the history for a second, Nagumo in 1942 gave necessary and sufficient conditions for forward set invariance. So this is really the key concept that we're playing with here is forward set invariance. Why? Because safety is staying within this set C. So that means you're safe if you stay in that set for all time. That is, if your system is forward invariant with respect to that set. And so the conditions that you came up with are very elegant. They're also very intuitive. And it's the following. If on the boundary of your set, and this is a very clear point to make, very important point, on the boundary of your set, if your system satisfies H dot being greater than or equal to 0, you're guaranteed to be forward set invariant. And this makes a ton of sense because if H being positive is safe, if on the boundary of the set, well, on the boundary of the set, H is 0. So if H dot is greater than or equal to 0, that means what? That H is going to grow or stay the same. And if H grows or stays the same, it has to be positive in the future. Hence, you're going to be forward invariant. So that's the essence. The key point, though, is this is necessary and sufficient, meaning it goes both ways. So there's no better condition out there. The problem and the missing piece, and this is what the 2014 result resolved, was this was only true, or these conditions were only given up to this point on the boundary of the set. But in the context of control, that's not a very useful condition. Because if you're sitting in this set and you know on the boundary you have to do something, how do you synthesize controllers in that context? And the answer might be, and what people have done is, well, when I get near the boundary, I'm going to switch to a controller that satisfies this condition, let's say. But then when are you going to switch? How are you going to switch, right? Is it a spatial switching? Is it a temporal switching? So all of a sudden that gets really messy, and I hate messy. So the better question might be, how do we extend these conditions throughout the entire set? Now, you might say, well, let's just enforce this everywhere on the set and call it a day. It turns out that would be the wrong answer too. Some people did that, but that's wrong. And that's wrong. Why? Because that's way too conservative. It's way too conservative because that would force, if you start inside the set, this would also force your function H to grow, which means that any smaller set you start with and you'd stay in for all time if you enforce this everywhere in the set. So what's the answer? Well, the answer is to modify the right-hand side of that by a little bit, just change it a little bit. And the change is this is a class K function. Actually, importantly, it's an extended class K function minus, but think about it as a constant if you'd like, times H. And what does this do? Well, this degrades, not in a bad way, but degrades to the condition on the boundary when you're on the boundary. So on the boundary, H is 0. So H dot is greater than or equal to 0, and we recover Nagumo's conditions. It turns out you can prove this not even using Nagumo. There's other ways to prove this as well. This is a nice paper that I have with Sam Coogan on this. But inside the set, what does it say? Well, if you're inside the set, H is positive, which means this whole term is negative, which means H dot can go negative, which means H can shrink. So that means that inside the set, you can actually approach the boundary. But as you approach the boundary, that shrinkage gets lower bounded ultimately by 0 as you get to the boundary, hence it keeps you in the set. So it's a really simple Lyapunov-like condition, but that simplicity, and this is it in action. This is a system, actually experimental results of a system doing this, where it gets to all the way to the boundary and the barrier function sort of pushes it there, and then the system dynamics pulls it back in. So that simple condition, though, gives you a theorem that's very similar to the Lyapunov theorem, where once you have one of these control barrier functions, you get an entire class of controllers that renders your system safe. Any controller that lives in this set defined by this inequality will keep the system safe. And then just like with Lyapunov, that allows you to synthesize controllers. But now this is actually a much more relaxed and flexible controller even than the Lyapunov controller gave us. Why? Because we have our safety condition here. And now this desired controller starts to mean something much more substantial. That is, you might have a PD controller or any controller you want that achieves the objectives of the system. And all we're doing is modifying that controller minimally in a pointwise minimal way so that we guarantee safety. And in fact, you can see that in the sense that you can write down the closed form solution for this quadratic program as something like this. And these terms themselves don't matter much, but the way to think about it is this is just a conditional statement where if your system is safe, that's positive, then you just do you desire. If your system is unsafe, this thing goes negative, then you take this minimal modification to make it safe. So that's control barrier functions. And this is how it looks in practice. So on the top, we have just a PD controller keeping the system upright. You kick it, it overshoots, it falls. And then on the bottom, that PD controller is filtered by this safety filter, this barrier function, this QP, which keeps it within this set. And in particular, I mentioned safety filter there, but that's kind of the way to think about this is you're given your whatever controller you have, and you pass it through the safety filter, which is just this QP, pass that to the system, and then you're going to modify the system in such a way that you get safety. So this is, again, the same scenario as before with now we have a barrier function in the spatial, not the upright position, where without the barrier, it violates safety all over the place. And with the barrier, regardless of what the operator is doing, trying to disturb the system, it will stay within this safe set. So that's safety. And that's the theory behind safety in 5 or 10 minutes, right? So now I can show you some applications of this, because this basic idea turns out to have been quite powerful. I hate to say that way, but it works really well in practice. And let me sort of tell you one more theoretical thing that's kind of interesting and I think conceptually important is it turns out that Lyapunov functions are specific examples of barrier functions, not the other way around. So we have a set inclusion of the class of all Lyapunov functions and the class of all barrier functions. In particular, Lyapunov functions correspond to barrier functions where your set is a point. And that's important for a couple of reasons. One is it says we've sort of, I don't want to say generalized Lyapunov because these are all Lyapunov-like conditions, but we've expanded our conceptual viewpoint of Lyapunov. And not only that, but this also implies that not only do barrier functions render this set forward invariance, but they also render this set stable. So you get stability to the set and set invariance within the set. So you get kind of this double whammy, and that's represented by these theorems. And the proof's actually super simple. You can come up with a Lyapunov function for the set from a barrier function. So there's this nice connection with Lyapunov in the end. Okay, so let's think about some applications of these ideas. And like I said, we've been working on this for a while now, and there's a bunch of collaborators that I've worked with, including people at Georgia Tech, Magnus Egerstad, Eric Ferrone, also Sam Coogan recently, people at UCLA, Paulo Taboada, people at Michigan, Jesse Grizzle, Gabor, also some companies, ETH. So there's a whole bunch of people I've worked with in this context, and I just want to show off some of these applications. So the first application is one, this is actually my postdoc did this experiment. He's now at NVIDIA. And we have a paper with some of the math in it also cited there. But this is just a cool example because it shows barrier functions in a very visceral way. So what's happening here is the barrier function is you want to keep the car in a lane. The human is you desired, that's the human. And the human's trying to steer the car outside of the lane. And the steering wheel on the left is the barrier function. So you'll see there's a mismatch between the human and the barrier function because the barrier function is keeping you in the lane, even if the human's trying to mess you up. So that's filtering through and this is even in snow. This was taken at Michigan, obviously not California. So more recently, we did a very similar thing with Gabor. This was also in Michigan on adaptive cruise control. So in this case, the goal is to keep a minimal distance effectively It's actually a time headway, but minimal distance between the lead car and, in this case, a truck. This is a full scale, like big rig truck. And this is running barrier functions. And it turns out that if you are running, sorry, it's not running a barrier, it is going to run barrier functions, but this is running sort of nominal controllers. And it turns out that if you use barrier functions as context and filter these controllers, even though we're using a really simple, like low dimensional representation of the system to synthesize the barrier, as long as we couple that with something we call tunable input to state safety, I recommend you check out this paper. We're able to guarantee safety, meaning that these things don't crash, even though we have this super complicated big rig truck with all these dynamics we're completely ignoring, and it works. And this is the safe distance that we get in the end. So those are two car examples. And the car examples can actually be put together into a single example, although this example predates the car examples. In fact, this was one of the first experimental examples of barrier functions in action. And this was with Magnus Egerstad at Georgia Tech. And this was on the Robotarium, or this is a precursor to the Robotarium, actually. So in this case, we have a bunch of mobile robots. And think about this as a combination of lane keeping, sort of, and adaptive cruise control. What I mean is you command these mobile robots to go straight across the room. And yet all the robots are being commanded the same way. So the reality is they'd all come and collide simultaneously in the middle, and it'd be just a massive crash. So instead, you take a barrier function that's sort of making sure that there's a distance, a buffer set around all these robots. It's a little more complicated than that, but that's the essence of it. And you implement that through the control barrier function, and this is what happens. So they're all going to this crash point, and then the barrier function starts taking over. So all of this behavior here that you're seeing is purely a function of the barrier function. And so they're sort of, it's like they have virtual force fields around them, and they're rolling off each other until they're able to move and spin around so they can get clear of each other, and then they continue to their destination. And the key point here, of course, is that none of this is planned, that we're not planning these trajectories around each other and trying to handle all this. This is just purely a reactive controller that gets you safe in the end. So the same idea, although albeit with more complexity, because we're actually using nonlinear dynamics and differential flatness, can be applied to drones. This was also work with Magnus, and Li Wang was a student that led all this effort. And in this case, Li Wang, is trying to drive this drone into these drones, which are autopiloting, and the barrier function is what's preventing them from colliding. So this is this is cool, and this was a great demonstration from like 3 or 4 years ago now. The question is, can we actually push these things in a context where we have more realistic scenarios? What I mean is, in this case, we're in a room, we have motion capture, everything's nicely constrained. Well, it turns out we can, and we have, and so this is a drone doing, in this case, collision avoidance, meaning don't hit this thing in front, but it's using an onboard camera now, so onboard sensing. And when my student here, who led this effort, takes away the obstacle, correspondingly, the barrier function is modified, meaning the value of the barrier function is modified, and the drone gets to fly. And I just want to kind of note really quickly for those that are interested, because I get this question a lot in these talks, well, what's the difference between barrier functions and potential fields? Well, it turns out potential fields is sort of think about it as a very specific case of barrier functions as well. I could go into a ton of detail on what that means, but in short, if you have a potential field, you can synthesize a barrier function, and this is what it would look like. Conversely, you can't do the other way around, because barrier functions are a more general class of systems. And finally, you can do, again, the same kind of thing, but now we have a human controlling this drone, and the onboard sensing is detecting the obstacles and avoiding them as it flies through this kind of maze filtered by the barrier function. So those are 2 examples. You might say, this is cool. Okay, fine. Now you're not using motion capture, but you're still in the lab. So we have a recent video that I think is really cool, where we've gotten rid of the lab too. And now we have a drone flying outside with onboard sensing, onboard computation, doing control barrier functions in real time. So just to kind of set this up, we're doing geofencing. What that means is we have this drone, and the goal is to not leave spaces, regions in space. So in that case, this region is here. And you can see it here too when it comes to this stop. So we have regions. So there's much more graphical illustration of the region. So, and we had a region here, a region here. So basically we put a box around the drone, and the pilot's flying the drone as fast as possible to the edge of the box. And the barrier function is running on board in this case using GPS as our sensor, to calculate where it is relative to that geofield and modulate the trajectory to make sure that the system is safe. So this is that one more time now that there's the context. And the important point here, and what I think is pretty incredible, is this drone is a high-speed racing drone that was sort of custom built by my students in my lab, and it's actually flying at 100 kilometers per hour. So that's like, for those that deal with miles per hour, that's over 60 miles per hour. So we're doing control barrier functions in real time with onboard sensing and computation with a drone flying at 60 plus miles per hour. That's why we have to really slow it down, and we have these little circles. It's hard to like show it now. And by the way, it's also cool. They flew this around the Rose Bowl, so the setting's pretty awesome. But anyways, so this showing that we really can do this stuff in practice. So there's the Rose Bowl. We can do this stuff in practical context, like outside the Rose Bowl, and implement it in real time. Okay, so now I want to sort of switch dates. So I'm going to go through a bunch of stuff now. I got a lot more videos to show, but the level is going to get a bit more abstract, high level. And the reason why is I want to communicate a broader sentiment. Now that we kind of did some detail, and I have to do a little detail on the math, the question is, what do we do with this, and how do we really bring this together in the context of autonomy? And to give this some context, this is the application of barrier functions on a quadruped for stepping stones. So this is actually the first implementation of barrier functions on a legged robot. And what it's doing here, this is the sim results, but what it's doing is, again, it has a nominal walking gait, and the barrier functions are modifying that gait to make sure that it can step on these stones and won't fall between them and fall. And so the location of the stones defines all these barrier functions. And the important point here is, to get this to work really robustly, we not only did the barrier functions at the real-time control level, but we also did it at the MPC level. So this robot, this is joint work with ETH, and this robot uses MPC based on some reduced order models to plan the walking gaits. And we also implemented barrier functions there in essence. And so what this is pointing to, and the reason I'm showing this is, it's cool that these barrier functions are working, but it also shows that to get these really complicated systems with complicated behaviors to start to be safe, we can't just do barrier functions at the real-time control level, but we have to start to bring in like slower control methodologies. And slower, I don't mean in a bad way, I mean at the level of planning and decision making. And so this sort of leads back to this big picture I showed you earlier. So I've covered this low-level control front, not to say I've solved all the problems, but I've at least set the stage as to what you can do in that context. So the question is, how do we understand now this in this broader context of how do we fuse this with high-level control, with planning, with everything else? So I'm going to give you some samples of what we're doing here. And a lot of this is still sort of work in progress, and we have papers on it, but it's still a framework that's starting to gel. So you'll see that a little bit in how this comes across. And so just kind of as an example, if you want this segue now to explore an unknown space. Well, we have some uncertainty in our samples. We have uncertain regions in space. We want to ultimately get to some science samples, some goal. How do we do this? Well, we can't just do a barrier function because, I mean, the barrier function will help you avoid these obstacles, sure, but we don't know if there's obstacles. The blue ones, we don't even know they exist. The regions, we don't know what's there. So we need to combine this with something, right? So it turns out we combine this, in this case, what you're seeing, and this was a TAC paper that we just submitted recently, is we combine this with PalmDP planning. So the planner explores the space subject to the uncertainty in the space, and then that passes down to trajectory generation at the MPC layer. This is trajectories for the segue. And then that passes down to a real-time control layer, which uses barrier functions. So we can bring all those three layers together. And the idea is, at least in this paper, we're able to make formal guarantees that the entire system is safe, let's say, and has the properties we want across all of these layers running at all these different timescales. And so why is that important? Well, it turns out that this was motivated, and I'll show some other examples of this in action in a second, but this was motivated exactly by this March 2020 mission. In fact, this started with work with JPL, where the idea was, how do we coordinate between the Mars, the rover, and the helicopter? And that the answer was, well, let's do MDPs, to Markov decision processes. And this is what we did, and we were able to do this mission coordination. And we even demonstrated experimentally where here's our rover and here's our helicopter. But what happened in doing this was I realized how inherently fragile all of those planning methods are when they don't account for dynamics, which they typically don't. And I don't mean that as a slight to people that do these. I just mean that they typically don't, because it's really hard to think about dynamics and you're doing planning all at the same time. And when I say fragile, I mean the following. It turns out that this worked, but worked one time out of about 150 trials. And every other trial, we kept having issues with drop sensors. We were using motion capture, and that would drop. And we'd have this, our drone just kept spinning off because it was losing sensor signals. And everything was just, we didn't have the right real-time controllers. And this thing kept crashing into the wall. My students actually rebuilt the drone so that it could fall apart and they could build it again quickly because it was breaking so much. So what does this mean? Well, we need to bring these layers together. This is what I'm sort of hinting at. And we have results doing this. I'll just be brief, but for example, as a quick example, we can take these Palm DPs, and it's well known, actually going back to like Colin Belta and others, and almost 10 years ago now, that you can represent these Palm DPs as discrete time dynamical systems, meaning this discrete planning layer can be represented as this dynamical system. And once you have that representation, you can take this idea and you can replace it with a discrete time barrier function on these discrete time dynamics and correspondingly come up with these safety filters for Palm DPs. So here we can enforce safety in that context. And this is what this looks like on a multi-robot system example. Again, the point I'm making here is at the planning layer, we can start to enforce safety. And we enforce safety conceptually in exactly the same way we enforce safety at the real-time control layer, except all these things mean something very different. So we're not minimizing the norm square, we're minimizing the expectation between the reward of one policy versus another, subject to discrete time barrier functions on the dynamics associated with the Palm DP. But we're able to do this in practice, and we're able to start to bring this together. So going back to this rover drone example, we have the rover and the drone now coordinating. Not only that, but we took away the support structure. So we have a drone, we have the rover here as an inverted pendulum segue. So it has some nonlinear dynamics of its own. And the way we're able to do that successfully is by bringing together MPC with this planning layer phenomenon. So what was missing here, the reason this crashed, is we didn't have the low-level controllers yet in the picture. But the point is that I'm making is that starting to go across layer makes things inherently more robust. And here's another example of this, where now we have, so think of this as a planning layer, motion primitives in this case. We have a trajectory generation layer, and we have a real-time control layer. And by pulling those pieces together in holistic ways, we're able to do things like run and jump and everything in much more dynamic ways. So finally, I want to show some, this is a recent paper we just submitted to RAL and ICRA. And this shows this idea, I think, even in more stark contrast. So in this case, we have a drone, and the setting's much the same. We have this drone, and we want to have this drone avoid these obstacles. So, and we're able to do that. The key here is we're no longer doing that using the full nonlinear dynamics of the drone, but rather we're doing that using the layered architecture. So we can implement barrier functions at different points in the layer and use the architecture to guarantee safety across the layers, regardless of the platform. So I just showed it on a drone. The exact same math works on a quadruped to avoid the obstacles, because we're now using the structural layered architecture to design this safety critical control method, rather than worrying about making sure that we even know the complete dynamics at this level. This can be taken care of the engineer, in this case, my grad student, who developed the walking controls. And we can start to piece these layers together in holistic ways. We can do that in a planning sense. So this is now the quadruped and a drone. And what they're doing is they're not only avoiding obstacles and things, but they're actually working together at a decision-making level to do things like that Mars mission, where now we have, not only did we get rid of, we have the rover is now a legged robot, and this is our Mars helicopter, if you'd like. So by playing across layers, we can start to exploit a lot of structure and get much more complicated behaviors. One final piece, just to mention briefly, is we can even bring machine learning into the mix here. And I mean that in a very constrained context. That is, in this case, we're actually doing onboard vision and self-supervised learning with an onboard camera on the quadruped. So what we're doing is we're learning the depth map. And by learning the depth map, we can pass that to the barrier function, which passes to the low-level controllers safe signals, and we're able to do safe interactions, for example, between this and a person or obstacles, using a layered architecture, all in sort of a holistic way. And again, just we did this experimentally, doing the experiments on the quadruped. We did it in like a couple days once we had the vision part set. So that's where the advantages of architecture come. So in summary, I think this layered approach is really powerful, especially when you couple it with good control theory at the low level, good trajectory planning at the mid level, good sort of formal methods at the discrete level, and then start to understand the interplay between these layers. And this, by the way, is a contrived video. This is the one, actually, this is the video that is like the one here. So there's nothing real happening here, just to be clear. This is not a scientific video. It's a conceptual video of what I'd like to do. These were my grad students, they were playing one day, and that's when I took this video, is they just were playing with the robots and driving at each other and sort of seeing, kind of terrified me a little bit. But this is what we want to do autonomously in action. Okay, so I have like very little time, but I want to pop through one more application domain quick, and because I think it's important to discuss the applications of these ideas to another real world scenario, which is robotic assistance. So I'll just say sort of briefly, if you'd like, how we're attacking this. Well, we're attacking this by saying, well, we have these great walking controllers, for example, on legged robots. We also have this layered architecture that's proving to be really effective on robotic systems. So how do we take all this and put it into a new application domain, new meaning for my lab, something like robotic assistance? And we've been successful in doing this now for a couple years. And just as an example, this trajectory planning layer, which is the way we generate walking gaits in my lab, we've successfully applied to an exoskeleton in collaboration with this French company, Wondercraft. And this is what that looks like. So we're using their hardware, but in essence, our math for trajectory generation. By our math, I mean me and other collaborators. And by doing that, we can generate stable walking for the exoskeleton. And this is a complete paraplegic using the device. So this patient has no function of his legs whatsoever. None of these patients do. And they're able to walk dynamically using the exoskeleton because the trajectories are generated in a way that guarantees dynamic stability. So that's just pointing to the need to bring this formal approach to other application domains. We've also done a similar translation at the level of control barrier functions. So we implemented control barrier functions on the exo. Now this was in my lab, and these are healthy subjects, that is grad students, but we're still able to implement barrier functions in a real-time fashion on the exoskeleton for variable assistance. That is to allow the person to do a little bit of work on the exo as long as they don't destabilize the walking. So finally, we've done similar things with prosthetics. So in this case, we can do trajectory planning, that is gait generation for prosthetics. We can also do real-time control, that is running the QP on prosthetics, the CLFs, the barrier functions, everything else. And the results are things like this. So this is actually running, again, a quadratic program in real time on the prosthetic using a model-based controller. So in this case, have my graduate student walk outside. So this is Rachel. She's done amazing work at this intersection of control and robotics. And so again, this is just under the surface of that prosthetic that she's using is all of the real-time gait generation things that we do for walking robots, the real-time control appropriately modified to prosthetics running in real time. So that's the how we can translate these things over. And we're working on a bunch of other application domains, things like doing real-time sensing, real-time force feedback, bringing some learning of force interactions into the mix. So there's a whole bunch of fun ways that we're thinking about expanding this paradigm. Sort of finally, I'm going to briefly mention another way we're thinking about expanding it. And I'll be quick here, but I think it's really important, is we can also think about bringing learning into the mix in very prescribed ways. So this is, again, the exoskeleton built by Wondercraft, but in my lab at Caltech. You can tell this video is taken by Caltech by the production quality. It's a very good video. But how do we understand how to bring this framework that I mentioned earlier together with prosthetics, together with the fact that we have human subjects and we don't understand what the human subjects necessarily are doing or want? And so my student, Megan, has developed, along with others, has developed this really powerful framework of preference-based learning for exoskeleton locomotion. And the idea is in a nutshell, you can ask the user what they prefer, and you can use this sort of ordered preferences of the user to learn their cost function, if you'd like. And more importantly, learn gaits that minimize their cost function, even though you don't know their cost function. So it's learning at this gait preference level, this high level, which we can then pass through these other layers of the architecture to realize on hardware. And just to show you some examples, we've done this learning at multiple places. So we've done it in terms of controller parameter tuning. That is, at the lowest level, we've taken our QP and we can do preference-based learning to determine parameters of the QP that give us the most robust walking on the system. We've done it at the level of gait generation. So in this case, what I'm saying is we're generating these gaits for the walking robot, and then the user, the human person, specifically the grad student, is sitting there saying which gait they liked better when they run an experiment. So everybody that's done experiments has done this before, and then picking the one they like best. And the end result is we're able to generate really nice walking gaits really quickly using the preference-based learning, even though we don't know the utility function of the graduate student and what they like about walking on a robot. They're just looking at it and saying, this looks like a good walking gait. And in fact, it looks like a good walking gait in the end. Finally, we can do this at the level of human preferences. So what I mean is we can pick between different gaits based on feedback from the person in the exoskeleton, and in a variety of different walking gaits. So we're looking at features and ultimately finding the gaits that they prefer the most. So this has been done on a whole bunch of subjects, but let me just show it in action. So this is a complete paraplegic again. This is testing done in conjunction with Wondercraft. So what we're doing now, just again to recap, is we're asking the subject when they run two gaits what they prefer. And based on that, we can sort of optimize the gaits through this preference-based learning to find the gait they like best. And again, these gaits are all generated using the same methodology that our walking gaits were generated. So the least preferred gait, you can see why it is probably least preferred by the user. It's not really stable, requires a lot of support. As this learning process continues, you get to the mid preferred gait, starts to look a little better. And then finally, we get to the most preferred gait. So this is what the preference-based learning gives, and it's a dramatically better gait, I think, than the one that was started with. So again, this is showing this interaction at all these layers together with learning in a very pre-prescribed way to pull all the pieces together into an application where we can actually use it on real patients. And sort of this idea of heading to real patients is something that I think is especially powerful. So this is a joint paper with doctors that perform these experiments, the company Wondercraft, where we documented the application of these ideas in a clinical setting with clinicians running the exoskeleton. By the way, just to be clear, not preference-based learning. This is just the gait generation part, but we want to do the preference-based learning ultimately. So this is kind of ultimately where we want to go, is take these ideas to a clinical setting on the robotic assistive front, meaning all this math should ultimately find purchase in real-world applications. So with that, this is the summary of what I talked about. So I covered a lot of ground. I can't really help myself because I think the videos are super cool and I want to show you as many videos as I can. So excuse the video bomb. And I have to talk a little bit about the math too. And that's kind of the key point, is the math is really the important thing here, not the videos. The videos are awesome to see. By the way, that's that root system I showed you earlier. And now we can walk over it just fine because we've made our methods better. And there's a close-up of the root system and you can see the robot handling it really well. The point is, it's through good math that we're able to do this now, not just a bunch of experimental work. So it's math as being the counterpoint. And the math I talked about was things like control barrier functions, multi-layer architectures. And it's really understanding that interplay that gave us the ability to do cool things like get robots into the real world. So, you know, this architecture that we're developing and the control barrier functions that are really the core, the safety critical things, are the essential part of making things like this happen, where now we have QP-based controls based on nonlinear dynamics and nonlinear control running on the robot in real-world environments, with the result being this just smooth, stable walking. And that's ultimately where we want to go with everything we're developing. So with that, thank you very much for having me.
Thank you so very much for that presentation. That was fantastic. Do we have any questions from the audience? We do have a little bit of time, a couple minutes. Again, there's a Q&A feature. If you go and put your questions there, we'll be able to answer them. You also want to use the chat feature and maybe to talk, I can unmute you. So we have a question from Nikhil. Maybe I'll allow Nikhil to talk and ask himself.
Oh, see there. I see the question in the. do you ever get into switching instabilities at border? I assume you're talking about like the boundary of your safe set and switching instabilities associated with that.
Right. Yeah. I was just wondering, like, if that ever happens, at the border, you go back and forth. Let's say, does it ever happen? Or you are mostly, let's say, for example, your drone example, when you were geofencing, right?
Yeah.
Does it ever go back and then hit the boundary again, or it moves? Does it, if it happens, is it possible to avoid it? Maybe it doesn't happen and maybe you have observed it, but is it possible for that to happen? Like,
so I suppose, in short, that doesn't happen.
Okay, great.
Not to say it universally doesn't happen, but the whole point of control barrier functions and the fact that you're checking the conditions everywhere on the set means that you have predictive power there. That's what it's doing, right? So meaning that as you approach the boundary of your set, you know you're getting to the boundary because of the derivative condition, and hence you start to modulate your control away from the boundary, not on the boundary. And that avoids all that switching phenomenon that you would get associated with like doing a switch controller. It also avoids the oscillations you get with things like potential fields, because in this case, you're not combining your cost with your safety constraint like you do with potential fields where you combine those gradients, but you just have the safety constraint as a single inequality in the QP. So you tend to not get oscillations on the boundary. You tend to kind of smoothly approach the boundary and then slide along the boundary or close to the boundary, depending on this, and then you head back out. And that's not to say you never could. I mean, if on the other hand, if you're if the operator was taking you back, and I mean, you could ram into the boundary, but that's about the only scenario where we'll ever see it. So even if you try to ram into the boundary and ram through, all that's going to happen is you go to the boundary and you just stop. Right. So we don't, you get really smooth behaviors in the end. You don't get oscillations. I mean, again, just the drone example here. Let me if I can, there we go. Just as the drone example, we can watch the video one more time because I think it's informative. Because if we were going to get oscillations, this is kind of the place where you would get them, right? I mean, this drone is going at like 60, 70 miles per hour. And actually, here's another shot of it. As you get to the boundary, just come up and sort of smoothly stop in this case. And you can see in the plots, quite smooth. And this isn't like a one-off. They actually only did this experiment like once or twice. I mean, this kind of worked. As soon as they got the sensors and everything working, it kind of worked. And I don't say that lightly, but we weren't like having a bunch of bad behaviors that we kind of threw away and just showed this. But this is kind of how it worked out of the box. It's very smooth.
Thanks. Great talk.
We have one more question. Krishna?
Hi, it's a great talk. I have one question. You have shown like you have used similar barrier certificates for like a bipedal robot, for quadrotor, in one case where they were able to follow the safety procedures.
Yep.
What if like, because of the dynamics, I might have a new safety requirement, or like how is the safety certificates? Can it be adaptable? Because if I change from like nonlinear system to linear system or some cases like that.
So you're asking, I think, two questions simultaneously. So first, the question is, how do maybe barrier functions change based on dynamics, whether you have linear, nonlinear, etc. And that's, I mean, the reality is the conditions are general to arbitrary dynamics. So as long as you satisfy the conditions, you're good to go. That isn't to say you're necessarily going to satisfy the conditions, right? I'm not saying if you take any function H, you pop it on your system, this is going to work. Like, life's not that easy, and I don't mean to suggest that. You have to make sure you have a valid control barrier function, right? So that gets to your second point, which is, well, as your safety constraints change and what they mean change, of course, your barrier function changes, right? So you have different barrier function representations of different safety requirements. These can be anything from simple ones to handcrafted ones to complicated ones, depending on the application and what you're trying to achieve. And that's really the engineering part of it. I'll say a couple of things. First, by and large, synthesizing barrier functions is like, as long as you don't care about input bounds a lot, as long as you're not dealing with the bounded input case, which makes things more complicated, synthesizing them is quite easy. Much easier than Lyapunov functions, by and large, because there's sort of weaker conditions on them. They don't need to be positive definite functions, all this kind of stuff. That being said, there are certainly caveats like input bounds. So in this case, the way we synthesize these barriers is using this backup set notion. This is a little bit more complicated procedure to make sure we can satisfy the input bounds and everything on the system. So again, it's application dependent in the end, just like everything in engineering. I will say there's a ton of good work on automatically synthesizing barrier functions, even from things like specifications. So if you have STL specifications, you can synthesize barriers. That's not my work, actually. That's places like, Magnus did work there, Demos at KTH, others doing great work in that context. So there's a lot of work now on how to synthesize barriers, how to come up with them, depending on your definition of safety.
Thank you so much.
Thank you so much again for the presentation, and thank you everybody to attend it. We have another robotics seminar. Well, every Friday we have another invited faculty speaker next week. Please join us then. And thanks for everything.
Great. Thanks for having me. It was a pleasure.